I am Manuel Franco Sevilla. I'm a professor here at the University of Maryland. And today we're going to do a simple yet quite powerful experiment, so-called the two-polarizer experiment, where the main performers are going to be these two polarizing filters that, as you know, they block light, but only light that is polarized in an axis orthogonal to the axis of the polarizer, which is indicated by this mark over here. And so the main elements are, of course, the two polarizers, this holder that will allow us to place the polarizers onto the holder and then rotate it as we desire, and then a source of light that it's called a diffuse light that emits unpolarized light, which truly is just a superposition of various light waves with all possible polarizations. So effectively, you have all polarizations coming from here, and we'll see what happens when we place the two polarizers. So first, let us place the first polarizer with the mark at the top so that it only allows for vertically polarized light. We're going to let me just show you. So this is the diffuse light. With the polarizer, it becomes a bit dimmer because we've blocked the light that is horizontally polarized and because they don't have perfect efficiency. And now I'm going to place the second polarizer, first with the axis in the same direction as this axis, and then I will rotate it 90 degrees, and so we will see what happens. But before I do that, you should try to think yourselves whether you think the light that will be coming through both polarizers will change, will increase, or will actually be blocked when you rotate it 90 degrees. So try to think a little bit about the dynamics of this problem, and then we'll continue. All right, so you thought that out, so now let's see. So we have one polarizer here. Light is vertically polarized because it's going through it. Now let's put the other one with the vertical polarization. And so what we can see is that pretty much nothing happened. It becomes a little bit dimmer because polarizers are never 100% efficient, but basically all the light that was able to go through one goes through the second one. Now let us start rotating this one. It's a bit hard to rotate, so I'm going to lift it a little. And so as we rotate it, we observe we are starting to block light now that is polarized in this direction. And as we go to 90 degrees, and so this needs to be very finely adjusted, so let me look. We see that the light is basically blocked. I cannot get perfect 90 degrees, but you see the main principle that now the light that was vertically polarized after going through the first polarizer cannot go through the second polarizer because its axis is 90 degrees. And so how does this work? Well, polarizers themselves can be done in several ways, but basically they have molecules that are stretched perpendicular to the polarizer axis. And so that allows electrons to only vibrate in that direction. And those electrons are going to cancel the incident wave by emitting another wave 180 degrees with respect to the incident wave. So all the waves that are orthogonal to the axis will be blocked, and only waves that have polarization in the same direction will be allowed through. And this is actually used in many places. You probably used it in 3D glasses, and you use it every day in your computer screens. Computer screens such as this one, you have two polarizers and an optically active material in between the two polarizers that rotates the light when you apply a voltage. But the key thing here is that the end result, the light coming out of the laptop, is polarized. So if you put a polarizer there, you can see that it blocks almost 100% of the light when you go to orthogonal with respect to, I mean, it depends, of course, also on the colors. They can have slightly different angles, but you see how this light is very strongly polarized. Okay, I hope you found that interesting, and see you next time.